Hello students. Welcome to the YouTube channel, Physics Simplified. Here, we will understand numerous concepts of physics from a numerical perspective. So, without any further delay, let's jump into the discussion. Topic of discussion for today's video: magnetic field due to a straight current carrying conductor. This is one of the numerous applications of Biot-Savart Law. In this problem, we have a current carrying long straight wire placed along the y-axis and carrying a steady current of 8 amperes in the negative y direction. A uniform magnetic field, vector B0 of given magnitude, is applied in the positive x direction. We need to find the total magnetic field at the given points, where all the points lie on the xz plane. Let us now identify the concept we need to solve this problem. We know that whenever current flows through a given wire or a conductor, a magnetic field develops around it. So, the total magnetic field at any of the given points will be the vector sum of the applied uniform magnetic field, vector B0, and the magnetic field due to the flow of the steady current through the straight wire. Let us now set up the steps and equation to solve the problem. The expression of the magnetic field due to a steady current flowing through a long straight conductor is given by B suffix wire is equal to mu0 I divided by 2 pi r. Here, mu0 is the permeability of free space, I is the steady current flowing through the wire, and r is the distance of the given point from the wire. The direction of the magnetic field produced by the flow of current through the long straight wire can be found by using the right-hand rule. Since the applied uniform magnetic field is in the positive x direction, hence we can write vector B suffix 0 is equal to 1.5 into 10 to the power minus 6 Tesla I hat. Before solving the problem, let us know the orientation of the magnetic field lines due to the flow of steady current through a straight conductor. See the diagram. If a steady current flows through a straight wire, the magnetic field lines produced around the wire are in the form of concentric circles. The current through the wire is into the page and is indicated by the symbol encircled cross. From the figure we find that the magnetic field vector at any point around the wire is tangent to a circle. Let us now observe the situation from the side. The right-hand rule gives the direction of the magnetic field due to a current in a wire. If we point the thumb of our right hand in the direction of the current through the wire, then our fingers curl around the wire in the direction of the magnetic field lines. So, the fingers of our right hand reveal the direction of the field vector, which we have already discussed, to be a tangent to a circle. If we consider any point to the left of the wire, magnetic field is perpendicular to the dashed radial line and is found to be directed into the page. If we apply this right-hand rule to the problem of the diagram, we will get the directions of the magnetic field due to the current through the straight wire. At point A, this magnetic field is directed towards the negative x direction. For point B, this magnetic field is directed towards the positive z direction, and for point C, this magnetic field is directed towards the positive x direction. Let us now solve the problem. For part A of the problem, the coordinates of the point A are given by 0, 0, 1 meter. The net magnetic field at this point is given by vector B suffix A is equal to vector B0 plus negative of vector B suffix wire I hat. The negative sign is in accordance with the direction of the vector B suffix wire at point A. Substituting the necessary expression, the equation modifies to vector B suffix A is equal to vector B0 minus mu0 I divided by 2 pi r I hat. Substituting the given data and simplifying, we get vector B suffix A is equal to minus 1 into 10 to the power minus 7 Tesla I hat. This is the answer to the part A of the problem. For part B of the problem, the coordinates of the point B are given by 1 meter, 0, 0. The net magnetic field at this point is given by vector B suffix b is equal to vector B0 plus mu 0 I divided by 2 pi r k hat. Substituting the given data and simplifying, we get vector B suffix b is equal to 1.5 into 10 to the power minus 6 Tesla I hat plus 1.6 into 10 to the power minus 6 Tesla k hat. So, the total magnetic field vector at point B has two rectangular components, one along the positive x-axis and the other along the positive z-axis. After performing the necessary calculation, the magnitude of the net magnetic field at point B becomes equal to 2.19 into 10 to the power minus 6 Tesla. If we consider the field vector makes an angle theta with the x-axis, then theta is equal to tan inverse value of the z component divided by the value of x component. So, we get this angle to be equal to 46.85 degree. So, vector B suffix b is inclined to the x-axis at an angle of 46.85 degree. This is the answer to the part B of the problem. Now, the final part, part C of the problem. The coordinates of the point C are given by 0, 0, minus 0.25 meters. The net magnetic field at this point is given by vector B suffix c is equal to vector B0 plus mu 0 I divided by 2 pi r I hat. Substituting the given data and simplifying, we get vector B suffix c is equal to 7.9 into 10 to the power minus 6 Tesla I hat. This is the answer to the part C of the problem.